It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, welcome to the second video in the second topic. Just before I get started, I need a word from our sponsor. Well said, that's all I can say. Alright, this is topic 2.2. This is on equilibrium and yield. We'll be going through this reasonably quickly today. There are quite a few YouTube videos that link into this topic as well. So remember, anywhere you see that YouTube little icon when you're going through the PowerPoint, you can click on that, you can watch a video which will expand upon that topic. Okay, so I'm going to start off by discussing the concept of equilibrium, but what I want to say is that it's really important that you have an understanding of factors that affect the rate of a reaction, because equilibrium and rate of reaction will tie in really well together. So if you've got a good understanding of our collision theory, remembering that in order for particles to react, they must collide with the correct orientation and sufficient energy, and you've got a good understanding of that, and then you can combine that with equilibrium, you'll do really well in the final part of this topic. Alright, so equilibrium is basically talking about reactions that can go both ways. Okay, so we use equilibrium arrows that look like this when we're talking about an equilibrium, and an equilibrium reaction, as I said, can go both ways, and we normally have an equilibrium in a closed system. So we've got an example here of an open and a closed system. So here's a beaker with some liquid in it. If there's nothing stopping that or covering the top of that beaker, this is what we call an open system. So the particles in here are free to evaporate out, alright, and there will be some in the air that will condense back downwards as well. However, what's going to happen is that the rate of evaporation is going to be faster than the rate at which the particles condense and come down into the liquid. So this will eventually all disappear, but it will slowly decrease in volume. It's not a closed system. Particles can enter and escape as they want. A closed system, however, has like a glass plate or cling wrap or something like that over the top, so the gas particles can't escape, and so as they evaporate, they condense and go back down, alright, and they're going to do it at an equal rate, so the volume is not going to change here at all. So that's what we call a closed system, so where particles cannot enter or escape in any way. So we've got a couple of equilibrium equations here. Right? This one is a physical change, going from gas to liquid, liquid to gas, which is what we've got here. Right? This reaction here, where we've got iron and steam producing iron oxide and hydrogen gas, is one I'm going to refer to a couple of times. All right? So it's good if you jot that down as we go through. So when we're talking about equilibrium, if there is no change in the macroscopic properties, so that's things you can see, we have reached equilibrium. And we describe equilibrium as that the rate of formation of the products is the same as the rate of formation of the reactants. Another way you hear it talked about is that the rate of the forward reaction is the same as the rate of the back reaction. Okay? So, if we've got just an initial reaction, so consider that one where we had iron plus steam giving iron oxide plus hydrogen gas, that sort of a reaction here, which is in equilibrium. If it is in equilibrium, the rate of formation of our products is exactly the same as the rate of formation of our reactants. So C and D can combine to form A and B, and A and B combine to form C and D. Now initially at the start of the reaction, there is no C and D present. Right? We've only got A and B, so the rate of reaction between these two is going to be fast. So this is this reaction here. It's a fast rate at the moment, that forward reaction. Alright, because we've got a very high concentration there, and as you know from the rate of reaction video, concentration is one of the things that can affect the rate. So higher concentration means the particles collide more often, more likely that there's going to be a successful collision with the correct orientation and minimum activation energy, which means there's a higher proportion of successful collisions per unit time. However, as the concentration of that decreases, okay, the rate starts to decrease. Now, the reaction of C and D, okay, initially is going to be very slow to form A and B because the concentration is very low. But as the concentration increases, the rate of reaction is actually going to increase, and we get to this point where the rate of the forward reaction is the same as the rate of the back reaction, and when we've got that, equilibrium has been obtained. Okay. Now, each equilibrium has what we call an equilibrium constant, or Kc value. Okay, the Kc is determined by doing concentration of products divided by concentration of reactants. Now I'm going to go through an example on the next one, but I strongly suggest if you want, you watch the YouTube video over here, okay, which will give you a good example of going through and calculating Kc values. And the important thing to remember is that there's no units. Because you've got moles per litre here divided by moles per litre, right, they cancel out. Okay, and we use square brackets to represent concentration, just as we do with pH calculations. So here we've got this one here, sulfur dioxide plus oxygen gas to get sulfur trioxide. Okay, a couple of things I should go through in terms of some rules. In a minute I will, but for the moment I just want you to see what we're talking about when we use this whole concept of products over reactants. Okay, so in this reaction here we've got our product of sulfur trioxide. So here it is here. I want you to start noticing some of the trends. We've got 2 out the front for our molar stoichiometric value here, and then we've got a squared here. Alright, we've got a 2 in front of the sulfur dioxide, which is down the bottom, and a squared. There's a 1 out front of the oxygen, so it's just the oxygen by itself. So the Kc value for this expression, or this equation I should say, is SO3 squared over SO2 times O2. Alright, similarly for this one, the Haber process, a 2 for the ammonia as a product, a 3 for the hydrogen as one of the reactants, because there's a 3 out the front, and a 1 for the nitrogen. Okay. Now this one works really well for both of these because all of these are gases, and I need to go through just a couple of rules around what we include when we're doing this equation here. There's a couple of things we do include, a couple of things we don't include. So the first rule is that if they're a solid or a pure liquid, they're not included in the Kc calculation. Now the reason for that is if they're a solid or a liquid, a pure liquid, so not aqueous. Aqueous is different, so when it's dissolved, it looks slightly different. Okay, I'm just going to lower that down so you can see this. So when it's dissolved in water, it's not a pure liquid, so you don't have a massively high concentration. When you're dealing with pure solids and pure liquids in reactions, generally the change in concentration for them is so minimal that they're always considered to be 1. So we don't actually include them in the Kc equations. So here we're coming back to this one between iron and water vapor. Alright, here it's a gas. Notice it's very important to gas. We've got iron oxide as a solid and hydrogen gas. So this one and this one, both of them will not be included because they're both solids. So all we're going to do is use the hydrogen gas as a product and the water vapor as a reactant. Here they are, both got a 1 in front of them, so they're just exactly like this for the Kc expression. Second rule is if you double the stoichiometric quantities, the Kc value is squared, and that makes sense if you follow through and do, if you put this one in the Kc expression from before, you notice that you square the hydrogen gas and you square the water vapor because there's a 2 in front of each of them, so overall it's squared. Okay, so we've doubled the values here from 1 to 2, 1 to 2, 1 to 2, 1 to 2, alright, so we square this value from 10.2 to 104.04. Final rule is if you reverse a reaction, you inverse the Kc value. Now hopefully that makes sense as well because Kc value is concentration of products over reactants. So if you flip the reaction around, you're going to end up with reactants over products, and so you're going to invert your Kc value. Alright, so here, notice this one back here. Alright, iron plus water vapor to form iron oxide and hydrogen gas. So iron plus water vapor are the reactants. Okay, if we make those the products, the Kc value is 1 divided by 10 over 2, so we inverse it, we flip it, and it becomes 0.0962. Now there's a lot that the Kc expression or value can tell us about the reaction. If it's greater than or equal to 10, the reaction is complete, so there's lots of products. Alright, and that makes it you've got a big number on top, very small number on the bottom, so high concentration of products. If it's about equal to 1, there's an equal concentration of reactants and products, which makes sense. If it's less than 1, the reaction is said to be incomplete. So you've got a small number divided by a big number, so there's lots of reactants, a small amount of product. Alright, so let's actually look at doing this. I said I do have one example here. So we've got this reaction here, hydrogen gas plus iodine gas to form hydrogen iodide. We've got 0.8 moles of hydrogen reacted with 0.5 moles of iodine in a 2-litre vessel. Now it's important that you take into account whether the reaction is telling you the concentration or the number of moles, because remember the Kc expression uses concentration values in there. So if there's 0.5 moles of hydrogen iodide at equilibrium, what are the equilibrium concentrations of hydrogen and iodine, and what is the Kc value? So best way to do this is always to put out a table using initial, go to, equilibrium. So this is our initial concentration. So for our hydrogen, it says there was 0.8 moles of hydrogen in a 2-litre vessel. So concentration is number of moles, which is 0.8 divided by 2 for the volume to get 0.4 moles per litre. Similarly for iodine, there's 0.5 divided by 2 is 0.25, and there's no hydrogen iodide initially. This section here is what you will fill out. So if I just actually go if I go back and I bring up my pen, if I can do that, hang on a second. Okay, so if I bring up a pen here, I'm just going to go in a blue color. So these ones here, these values you put in later. Okay, the only things that you actually put in are your initial values. So these ones here we get from the equation up here, and we also get there is 0.4 moles of hydrogen iodide at equilibrium. So this is the other value that we put in. Okay, so the green ones are our starting values. Okay, and we use those to fill in the blue ones in the middle. So you can see here we had 0 moles of hydrogen iodide to begin with. We end up with 0.2, so we must have added 0.2. Okay, now what we do is we use the mole ratio of the equation. Up here there was 2 moles of hydrogen iodide. So if we've increased it by 0.2 here, alright, if we've increased it by 0.2, the mole ratio is 1, 1, 2. So these numbers down here need to match it. Watch, 1, 1, 2. But this is a product. This has gone up by 0.2. These have gone down. Alright, so this is down by 0.1, 0.1. So now we take our values here. Okay, we take 0.1 off to get our equilibrium value of 0.3. 0.25 minus 0.1 gives us 0.15. What we do is we take these values over here into our equation. Alright, so hydrogen iodide squared over hydrogen times iodine. And we use 0.2 squared over 0.3 times 0.15, okay, and we get a Kc value of 0.89, which is less than 1, which tells us that this is incomplete or it favours the reactants. Now I know I've gone through this pretty quickly, but as you can see over here, I'll actually get rid of my pen now. Okay, whoops, come back, sorry. And what I'll do is there's 2 videos here for YouTube. Alright, both of these, and I'll just hold that in there for a second in case you don't have the PowerPoint so you can see which ones I'm talking about. So there's this YouTube video, or there's this YouTube video here. Both of those I go through different Kc calculations in a bit more depth, and I'll show a lot of examples. So I strongly recommend if you need a bit more help, you actually look at those ones as well. Alright. What we're going to do is we're going to go on to have a look at Le Chatelier's principle, and I'm actually going to stop this one here because otherwise I think this video is going to be quite long. So I'm going to stop this first section here at about 12-13 minutes. I want you to make sure you understand the concept of what equilibrium is and how to calculate Kc values before we go on to the next videos. Okay, thanks guys.